Okay, now we can start. Good morning, everyone, and also good afternoon, and probably good evening to all of you in different time zones. My name is Edi Tribaskoro. Welcome to the 8th edition of Combinatorics today's series. We are very happy to see you again. We are very grateful to welcome to the Dean of Faculty of Mathematics and Natural Sciences, ITB, Professor Wahyu Sri Gutomo, for the constant support of this event. Our big welcome to today's speaker for this event, Professor Martin Grohe. He is a professor for theoretical computer science at the RWTH Aachen, Rheinisch Westfälische Technische Hochschule, Aachen. I hope my pronunciation is correct. And we are very lucky and grateful to have him as our speaker today. Our big welcome also to all colleagues and students for attending this program. Thank you so much for your enthusiasm, and we really appreciate it. Hello, Professor Grohe. How are you today?
Yeah, I'm very good. Thank you. It's a pleasure to be here.
Okay, so thank you for accepting our invitation to give a lecture in this series. We believe that your schedule are very, very tight, but you managed to allocate your time for us. So thank you so much. And I'm glad to say that the registered participants for today's program are not only from Indonesia, but also from various neighboring countries, from Malaysia, some of them, and then from Thailand, Philippines, India as well, and probably from other countries. And I should mention that this program is organized by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi, Bandung. And now we are all very excited and honored to have Professor Martin Grohe from the RWTH Aachen, Germany, to deliver a lecture. And the title of his lecture will be The Logic of Graph Neural Networks, and will be chaired by Dr. Finney. But before I give the control to Dr. Finney, I would like to invite the Dean of the Faculty of Mathematics and Natural Sciences, Professor Wahyu Sri Gutomo, to give a welcoming speech. Professor Wahyu, time is yours.
Thank you, Prof. Edi, Pak Edi. Actually, I would only deliver a short speech. First of all, I am extremely overwhelmed to get this opportunity to welcome all of you to another Combinatorics today's series. Now it's number 8, if I'm not mistaken.
Yes.
Congratulations to Professor Edi and others who keep maintaining these sessions from the first one until today. And I would like also to express my sincere gratitude to Professor Martin Grohe for your willingness to be here among with us, to be here and giving a lecture on the logic of graph neural networks. And this is part of our efforts to be more engaged in international collaboration in terms of webinar, research, and other activities. And I hope that everyone here will get the benefits from your speech in terms of new information or insight of the in mathematics or combinatorial aspect, as well as this even become a bridge for our young researchers and students to get involved in some topics related to combinatorics, which is also important to them to have such kind of engagement with the professors or lecturers from abroad. I think that's all, Pak Edi. And once again, thank you, Professor Martin, for your time. And we are looking forward to following your lecture. Thank you very much. Enjoy this event. Good afternoon, everyone.
Okay.
Thank you.
Thank you, Professor Wahyu. And now before I'm giving to Finny, probably we should have a group photo first, because this photo will be a very important one. Okay. Now let's say, Pak Yusuf, can you help us to take a photo, group photo? Yeah.
Yes. I need to remove the spotlights first. Okay. Yeah, okay. I will only capture the one who turn on the camera.
Okay.
So please turn on your camera. There are 36 participants.
Okay.
Okay. Okay, I'm gonna take a picture, so everyone smile.
Yeah.
Yeah, okay.
Oh.
Okay, we can continue.
Okay, thank you, Yusuf. And now I'd like to ask Dr. Finney to share this session.
Okay. Thank you, Professor Edi. Good afternoon, everyone. I'm Finny Oktariani from Combinatorial Mathematics Research Group, and I will chair today's session. So in today's Combinatorics today series, our speaker will be Professor Martin Grohe from RWTH Aachen University. Before we begin the talk, I will read a brief curriculum vitae of Professor Grohe. Okay, let me share the screen. So Professor Martin received his doctorate from Freiburg University in 1994 and also spent his time as a visiting scholar in Stanford University and in University of California at Santa Cruz. So he's now at the Department of Computer Science at the RWTH Aachen University in Germany. But before, he also held positions at University of Illinois at Chicago, University of Edinburgh, and Humboldt University at Berlin. And Professor Martin also has published a lot of articles, more than 175 articles in reputable international journals. and he also has authored these books and lecture notes, as you have seen on the screen. And Professor Martin also has received various awards. He has received Hans Mayer Leibniz Prize by the German Research Foundation in 1999. And in 2018, he was awarded ASEAN Fellow for contributions to logic in computer science, database theory, algorithms, and computational complexity. For today's talk, he will give a talk about the logic of graph neural networks, a very interesting and a very popular topic recently, right? Okay. So during the talk, for the participants who have questions, can write your questions. You can write your questions in the chat box. Okay. So without further ado, I will invite Professor Martin to give the talk. Okay. Professor Martin, the time is yours.
Okay. So I hope you can all hear me well and see my slides.
Yes.
Good. So I'll speak about the logic of graph neural networks. Maybe not the most obvious topic for a combinatorics seminar. On the other hand, it's for me, this whole area is very interesting because the way from theory and mathematics to real practical applications is very short here. So in my university, I'm suddenly, since I'm doing some work on graph neural networks, in high demand. So I work with people in chemical engineering and in medicine and physics, and they all have an interest in this stuff. And on the other hand, we'll see that there is some real mathematics and some interesting connections to different areas of mathematics. So I like this topic, and I hope I can convince you to like it as well. Okay, so let's see. I need to move my slides. That's somehow, okay, now it works. All right. So in this talk, I'll speak about the logic of graph neural networks, and the motivation for looking at this is something that is sometimes called neuro-symbolic integration. And what is meant by this is that in traditional artificial intelligence, the main methods were rooted in logic. So knowledge was represented by logical theories. Logical inference was used to reason about the knowledge. Now, in the last, I don't know, 10, 20 years, we've seen a shift or a very high emphasis on machine learning methods. So these are essentially statistical methods. We look at correlations between different distributions and use this to reason about data. And both methods are quite successful. I mean, these days everybody talks about deep learning and machine learning, but actually the logical reasoning methods still have a lot of impact and are used in practice, for example, in formal verification of hardware. This is all rooted in logical reasoning techniques. So we have these two methods, both quite successful in their ways. But we would like to bring them together, and also conceptually this makes a lot of sense. On the one hand, we have a lot of data, so we can use statistical methods to reason about these data. This is very plausible. On the other hand, we have a lot of formal knowledge and we can reason logically, so we should not just forget this and only look at the data and derive correlations. So we would like to bring the two together, and that's what is meant by neuro-symbolic integration. It's an open research question. You see many people talking about this. and you see very few solutions. I haven't seen any really convincing solutions. But although I absolutely think this is a very important research task, and you can broaden it. There's also in the natural sciences traditional model-based methods for reasoning, simulation techniques, and so on. And again, you have the data-driven techniques from statistics and machine learning, and you would like to bring the two together. And I see this as a closely related question. So that's the broad background. Now, what I'm going to do today is somewhat less ambitious. I don't really know how to bring the two together, but at least I'm trying to understand the interface. So how can we go from logic to neural networks and back? And I'm specifically looking at graph neural networks, which I will tell you in a minute what they are. I think they offer a very flexible mechanism for applying machine learning methods. I think that's why they are so popular. And that also makes it maybe a bit easier to connect them to these traditional logic-based methods. So my talk will have two parts. The first, I will try to understand the logical expressiveness of graph neural networks. That means which logical concepts can I describe by graph neural networks. And the second part is the other way around. I'm trying to understand how we can use graph neural networks for logical reasoning, and I'm applying them to a specific formalism that plays an important role in artificial intelligence, so-called constraints satisfaction problems. And again, I'll tell you what they are. And then I'll just show you a graph neural network-based solver for such constraint satisfaction problems. So the first part will be mostly theoretical, and it will be much longer. After all, this is a mathematics talk. The second part is fairly practical work. So let's see. Let me explain first what graph neural networks are. So they are deep learning architecture for machine learning problems on graphs, okay? And you can see them as a generalization of convolutional neural networks. Now, I don't know if you know what they are. They are basically the neural network architecture of choice for processing images, for example. And images you can just see as grids, pixels on a screen, where at each point you have a few values, for example, describing the color of that point. So that's the structure you have. You have this fixed structure, and convolutional neural networks exploit this. Now in graphs, you have a more flexible structure. Grids are special graphs, but graphs have very different properties. For example, nodes can have different degrees and so on, and you have to accommodate for this. But what I think is an even more important difference is that in a grid, you have a clear orientation. So the neighbors are also in some sense oriented. The least you have is the cyclic structure of the neighbors of a node. In a general graph, you don't have that. You can't say, this is my first, second, third neighbor in any possible way. And also, if you have one neighbor, you can't say what the next is or something like this. Okay, and we have to deal with this. And that's actually, it's a trivial observation, but it's at the core of many problems you have when you try to apply more traditional deep learning methods to graphs. For example, one thing you could imagine to do is just take the adjacency matrix of a graph. So that's just a 0-1 matrix, and then apply whatever machine learning method you have to this adjacency matrix. And the difficulty, this doesn't work very well in practice. The difficulty is that by writing down an adjacency matrix, you implicitly order the vertices and so on. And then This is not information about the graph, but just information about the representation. But the machine learning algorithm doesn't know this. So it learns things about the representation where it should learn things about the structure of the graph. Okay, that's something to keep in mind. Now, as I said, GNNs have a wide range of applications in computational biology, chemical engineering, physics. I'm involved in some of these myself, and that's also a nice aspect of this work. Okay, now they are very popular topics, and you see hundreds of papers appearing every year, and honestly, it's very hard for me to keep track. And in the end, I'm still a theoretical computer science and not someone who's mainly working in machine learning. But there is a certain core architecture, which is known as message passing graph neural networks, or sometimes aggregate combined graph neural networks. And I will talk about this core architecture. We'll try to understand this. But there are really hundreds of variants where people add additional features and then empirically evaluate how they work and maybe find that for particular applications, they have advantages. We just look at the basics. Okay, and the basic message passing graph neural networks work as follows. So here we have a graph. We have 6 vertices, and what the graph neural networks do is they basically implement a distributed algorithm where the nodes of the graph, the vertices of the graph, also correspond to the compute nodes. And the algorithm is a message passing algorithm, so it proceeds iteratively. And in every round, all nodes send messages to their neighbors, and they receive messages, and then they update their states. So at any time, every node has a state, and the state is just a vector of real numbers. Okay, so initially, we have some initial state, say the all ones vector at all nodes. Okay, and then the nodes in the first iteration of the algorithm send messages. And the messages are also vector valued. So here node 1 sends a message to node 4. This message happens to be just a projection of the state on the first 2 coordinates. It can be anything in principle, though usually it's obtained by a linear function from the state vector. Okay, so not only node 1 sends a message to node 4, but all nodes, okay, now send messages. So node 4 sends back a message, and all the other nodes send messages. Okay, and then every node receives the messages of their neighbors in no particular order. They have just all the messages, and they aggregate these messages and combine them with the old state and compute a new state. So let's say this is the new state of the node. All the other nodes do the same thing. And okay, now we're in this situation. They all have their new state. They send messages again. They update their states and so on. And we can run this for as long as we want to. Okay. And then after some time, we may stop. And now still all the nodes have states, but we want to compute some function either on the graph or on the nodes of the graph. And now we somehow have to extract the function values from these states. Okay, that's essentially what we do. Let's do the same thing a bit more formally, just to set the stage for what follows. So let's first look at a graph neural network N with D layers. So we want to do D iterations. And what it does, as I just described, it maps the graph to a sequence of functions going from the vertices to some Euclidean vector space, okay, R to the P. Finite dimensional space. Usually in practice, it's something like 64 dimensions, or maybe depending on the size of the graph, up to 128 we have used, but you can do whatever you want, okay? So, and after initially we have states zeta 0 at every node, and then we iterate for d rounds, okay? So we have this initialization, and in my example, I just said, okay, all nodes have state constantly 1 initially. Now, if we have node labels, which usually we have in practice, almost always we have additional information at the nodes of a graph that we want to take into account, then we encode these node labels in the initial state in some way. Okay, and then in each round we do the following 2 steps. Well, every node receives the messages from all the neighbors. And in our abstraction, we can just say the messages are the states of the neighbors. That mathematically, it doesn't make a difference. In practice, it makes a little difference, but for us now, that's okay. So here I have a multi-set, because it may happen that a node has several neighbors that have the same state, and I want to take this into account. And we aggregate all the values. So this aggregation function should be a symmetric function, so not impose any order of the neighbors. So typically we would take just the sum of all these vector valued states. We could take the mean or the maximum, pointwise maximum, and we can apply it directly to the states of the neighbors, as I said here, or we can first apply some learned linear function. And when I say learned, this linear function has parameters, and these parameters I learn by training my neural network. I'll briefly come to that. Okay, we can even take some more complicated function, but in practice, usually this doesn't buy us anything. Okay, so the complicated functions are coming in the next step. And actually, it can be shown that some summation is completely general as aggregation function. So we just sum the vectors and we'll be fine. And then we have the next function, the combination function. And the combination function takes the aggregate value of all the messages and combines it with the previous state. Now, this is usually a more complicated, a nonlinear function, which is computed by a feed-forward neural network. Okay, that's where the neural networks actually come in. And often we don't just use plain neural networks, but more complex neural network architectures. In particular, we want to add something like memory to these neural networks, because we have the sequence of states at the nodes, and the evolution of this sequence should tell us a lot about the graph. That's the idea. So here we apply some kind of neural networks to update the states. Okay, that's basically it. So now we have, well, this update function. I just summarized it here. That's what I just described. And now we have to decide, what do we actually want to compute? And there's 2 things we may want to compute. One is node level functions. So in the end, we want to have a mapping from the nodes of the graphs again to some real vector space. I'm just assuming that the value space of my functions is a vector of real numbers. Otherwise, I encode the values somehow by real number vectors. So that's general enough, but it's a different dimension than the state. Usually the state is higher dimensional than what we're actually interested in. And well, to get this, the actual function value, we apply a readout function. And this readout function is again computed by a neural network. Okay, and that's something, the parameters of this neural network is something we learn when we train the graph. Okay, just a little piece of notation, since it's awkward to use all these parentheses, I'm just writing it this way. So that's a bit easier to read, I suppose. Okay, so that's node level functions. As I said, typically readout is computed by a neural network, and then the other thing we could do is compute graph level functions. And then we first have to aggregate the final states at all the nodes and then apply some readout function. Okay, and graph level functions could, for example, be, so in one application we try, our graphs are chemical molecules and that are supposed to be fuels. Okay, so chemical engineers in our university try to design biofuels. So so there we build a model that tries to predict the octane values of these molecules. So we apply the graph neural networks, do the iteration, and then in the end, we just have to extract a single number. And that's what's happening here. Okay. So we have these two kinds of functions that we may want to compute. Okay. And again, this aggregation function here is summation typically, and then we apply a feed-forward neural network to extract the value that we want. Okay. Two very important properties of these graph neural networks, and that relates to what I said earlier when I compared it to the convolutional neural networks operating on grids, on images, is an isomorphism invariance. Okay. So let's first look at graph level functions computed by graph neural networks. They have the property that for isomorphic graphs, the function value will be the same. And that's something that should happen, but one has to be careful. It doesn't always happen. For example, if we apply a neural network to the adjacency matrix of a graph, it will not automatically happen. Okay, but here, because everything is completely invariant, the single steps, we have this property. And we have the same for node level functions. There we would call it equivariance and write it as follows. So let's say we have this node level function. Then for isomorphic graph G and H, and for all isomorphisms between these graphs, and for all vertices, the function value at vertex V in graph G is the same as the function value at vertex H of V, so the image of V in the graph H. Okay? So these are important properties and desirable properties. Now, there's one more issue that I want to discuss, and then I'm done with my description of graph neural networks. So we have described graph neural networks as saying we have a fixed number of layers, that was D, and on every layer we apply these aggregation and combination functions, and they may be different functions for every layer. Okay, so in practice, we set up the architecture, and all the functions that are involved are computed by, are neural networks. They have parameters, and then we apply, we have a data set, and we train the parameters using machine learning methods, gradient descent methods. So basically, we have a minimization problem to solve. We want to find the parameter values that minimize the difference between the function computed by our graph neural networks and the true values that we know for our training data. Okay, so we can do this on every level. We have a separate function, and that's fine. Now, if we want to do many iterations, that's a lot of functions and a lot of parameters we have to learn, and that may not be ideal. Also, we may want to say, okay, if the graphs are larger, we need more iterations. So how do we account for that? We may not even know when we do our training how large the graphs can get. Well, there's another idea that we can use, and that's what we call recurrent graph neural networks. And there we just say, okay, we only have one set of functions. Okay, one aggregation function, one combination function, and we apply it over and over again for as long as we want. So we do an iteration that looks like this. We have a single aggregation function and a single combination function, and then we just apply it recursively. So we start from the initial state, aggregate with our one function, combine with the old value, we get the new value, the new states. And then we repeat this, okay? For as long as we want to. That's the nice thing. And we can decide at runtime, okay? So the number of iterations is not fixed. We can run for as long as we want and decide to stop whenever we want. So we can say this depends on the size of the input graph, how many iterations we do. It can even depend on the evolution of the sequence. For example, we could say if the sequence starts to converge to some value, we stop. Although there's no reason this sequence is supposed to converge, and we never require convergence, right? We just iterate this and stop. Usually it will not converge, and it doesn't have to. Okay? So, however we decide, maybe the easiest is just to look at the size of the input graph. Then we stop, and once we stop, we apply the readout function again, and we get our value. Okay, so this is how this works. So we have a learning phase where we want to determine the parameters. There we need data, graph-based data, to train our neural network. And then once we have this, it's basically a graph neural network is something like a distributed algorithm. Okay, it's a simple algorithm, but I mean, this is a general view on machine learning. What we do is instead of programming computers ourselves, we learn algorithms. Okay, and here we learn message passing algorithms. And now we want to ask, what can we do with these graph neural networks? And when I say expressiveness, what I mean is which functions can we compute in principle? Which functions on graphs can we possibly compute with these graph neural networks? Okay, that's the question we want to address. And we will answer this question in terms of logic and in terms of combinatorics. So now combinatorics comes in finally. After all, I'm speaking in a combinatorics seminar, and I want to speak. Actually, I'm going to digress from the main topic, from the graph neural networks. I want to speak about the so-called Weisfeiler Leman algorithm. Okay, and actually, I'll start with a variant of this, the so-called color refinement algorithm. It's an old algorithm that was invented as a graph isomorphism algorithm in the early 1960s, and actually it was reinvented many times in different areas. Okay, so in logic, in chemistry even. So in all kinds of areas, people came up with this algorithm. That's not surprising because it's very simple. And what it does is it colors the vertices of a graph with the idea that different colors should tell us that the two vertices are structurally different within the graph. Okay, and what would make two vertices structurally different? Well, a very easy criterion is different degree. If two vertices have different degrees, they are clearly different. There cannot be an isomorphism mapping one to the other. Okay, and now the idea of the algorithm is just to apply this degree argument iteratively. So the way it goes is that initially we say all vertices get the same color, and then in each refinement step, two vertices get different colors. If for some other color that is already there, the two vertices have a different number of neighbors. Okay, so after each iteration, we have a partitioning of the vertices into color classes. And once this partition stays stable, okay, we don't add any new colors, we stop the process, and then that's our final coloring. And I want to show you a quick demo of this. So let me see if I can find it. I thought I had it somewhere. Here. All right. So you see this now, I hope. So what we have here is, let me move this a little bit. It's just some graph, some randomly chosen graph. And we want to apply the algorithm. So initially you see all vertices have the same color. And now let's see. Here we have a vertex with 2 blue neighbors and a vertex with 3 blue neighbors, and they should get different colors in the next step. And indeed they do. Here we have this greenish node, and this one is, what is it, pink or red, however it shows up on your screen. Now let's see, we have these two pink nodes, that one here and that one. And one has, well, 2 neighbors in different types of green, whereas the other one doesn't have any green neighbors. So in the next step, they should get different colors, and they do. Okay, and now we again look at vertices of the same color and their neighbors. So for example, here, all these still have the same color, but this one has a neighbor in a different shape of orange than this one. So in the next round, they get presumably different colors. Well, the colors are starting to get hard to distinguish. Anyway, we repeat this, and at some point it stops. We can apply it again and again, but the coloring doesn't refine anymore. Okay, so now we have this coloring. So when nodes have different colors, we know they are somehow different. We know there cannot be an isomorphism mapping one to the other. That's the important thing. Okay, so let's go back to my slides. Where are they? Here. Good. So the section is called, just a remark, Weisfeiler Leman algorithm. And indeed, I will tell you what Weisfeiler Leman is in a few minutes. A color refinement is essentially the same as one-dimensional Weisfeiler Leman. There is a subtle difference that is actually even relevant in this context, although people usually don't pay attention. But I'm using color refinement here just to be on the safe side, although it really doesn't make much of a difference. Okay. So let's move on. One thing that is nice about the algorithm is that it's extremely efficient. We can compute the stable coloring. Well, if you do it naively, it would probably take something like time number of edges times number of vertices. So you need n iterations. In each iteration, you need about number of edges, many steps to refine. And if you're clever, you can bring it down to almost linear. So number of vertices plus number of edges times log number of vertices. So that's a nice trick. I don't want to get into, but it's really an extremely efficient algorithm. And that's why it's used, for example, as a subroutine in all modern graph isomorphism tools. So you have this running time with a log factor. At some point we ask, can we get rid of the log factor? But actually we can't, at least not for a very broad class of algorithms. That's something we showed a while ago. But still, it's a very good algorithm also from all practical viewpoints. Okay, how is it used as an isomorphism test? As I said, originally it was introduced as an isomorphism test. And this goes as follows. We say that color refinement distinguishes two graphs if their color histograms differ. That is, if some color appears more often in the first graph than the second, or the other way around. Okay, then we know they are non-isomorphic. Okay, if they have more red vertices, one has more red vertices than the other, since the colors are isomorphism invariant, we know the two graphs are non-isomorphic. Now, if the coloring is still the same, if the color histograms are the same, we don't know anything about the two graphs. Okay, so it's an incomplete isomorphism test. But still, on almost all graphs, it works in a strict mathematical sense, probabilistic sense. That's a result due to Babai, Erdős, and Selko from 1980. On the other hand, it also fails on very simple graph. If you look at these two graphs, so what would color refinement do? Initially, all vertices have the same color, blue. And now every vertex in both of the graphs has two blue neighbors, so color refinement does nothing. Doesn't partition the vertices. So they stay blue forever. And color refinement cannot distinguish the graph. Both graphs have 6 blue vertices. So color refinement can never tell them apart, even though obviously they are not isomorphic. They are structurally different. Okay. So one nice thing about the algorithm is that it's so efficient. That's important for practical purposes. But it's also extremely interesting from a theoretical point of view. And that's something that we all have only fully understood in recent years. It has many connections to other areas, which are completely surprising and not at all obvious. And I summarize these connections in this theorem without telling you too much about them. But starting from this, we have done some really interesting research in recent years that quickly went into some fairly deep mathematics. For example, representation theoretic techniques play a big role. And that's the interplay between such combinatorial phenomena like the color refinement algorithm, logic, and then homomorphism counting plays an important role, and I'll show you the connection. So we start from the following. We have two graphs, and we say we have a number of equivalences, and the one we start with is that color refinement does not distinguish the two. They look the same to color refinement. That's the case if and only if the two graphs cannot be distinguished in the logic C2. Now that's a somewhat weird logic. It's the two-variable fragment of first-order logic with counting quantifiers. Now that may not seem as the most natural logic, but actually it's a logic that has been studied for a long time in an area called finite model theory and plays an important role there. So that's a well-known and well-studied logic. So the next characterization is algebraic, and basically it comes out of the idea of solving the graph isomorphism problem using linear programs. Okay, and the result is, okay, basically look at this equation. We have the adjacency matrices of the graph, and we say that it commutes with the matrix X. Okay, and imagine X is a permutation matrix. Then this essentially means that we can, well, we maybe multiply with the inverse of X. So we permute the matrix, the adjacency matrix of the graph G to obtain the matrix of the graph H. And that means this permutation matrix would just encode an isomorphism. Okay, so they are isomorphic if there's a permutation matrix. But that gives us a system of equations or inequalities for graph isomorphism testing, but that doesn't help. However, if we look for rational solutions, then we would relax permutation matrix that has exactly one value in every row and column, to doubly stochastic matrix. That's a matrix with non-negative entries where all the rows and columns add up to 1. Okay, that's what we call fractional isomorphic. And two graphs are fractionally isomorphic if and only if color refinement does not distinguish them. I think a very pretty result. And the last result is a combinatorial one. We count homomorphisms from trees to our graphs, okay, for all trees. And if the numbers come out the same for all trees, that's equivalent to color refinement not distinguishing them. So we have these three alternative characterizations of the equivalence relation, and they seem to have nothing to do with each other, but actually they are all equivalent. So that's very nice, and this can be generalized, as I said, and leads to a very nice theory. Okay, now let me briefly mention in one slide that there's also a higher dimensional version of this algorithm. And what we do there is we color k tuples of vertices, not just single vertices, but tuple of vertices. And we do this in a similar iterative way. For example, here you see the coloring we get when we apply this to a cycle of length 8. Okay, now that of course costs a lot more time. So the running time will be number of vertices to the k plus 1 times log n. The one-dimensional version is essentially the same as color refinement. The k-dimensional version is much more powerful as an isomorphism test, but it's still not complete. That can be shown. But for example, it can distinguish even three-dimensional Weisfeiler Leman, can distinguish all planar graphs. Okay, and then we have these characterizations of color refinement in terms of logic, linear inequalities, homomorphism counts, and all these characterizations can be generalized to the higher dimensional versions. Okay, so much for the Weisfeiler Leman algorithm. Now let's go back to the graph neural networks. Okay, let me quickly remind you what they were. We have these message passing protocols on the graphs, we have the states, and so on. Okay, initially, the initial state just encodes the label of a node, then we aggregate, combine with the old state, and in the end apply a readout function either at the node level, we want to compute a function on the nodes of a graph, or at the graph level. Okay, so I put an index here in the notation to refer to the graph neural network, and now I don't know what's wrong. Anyway, or we apply it at the graph level. Okay, so that's graph neural networks, and let's just jump into the first and maybe main result of this this chapter. We add one equivalence to this previous theorem on color refinement. Color refinement distinguishes the two graphs if and only if they can be distinguished by a graph neural networks, or in the previous theorem I phrased it the other way around. Color refinement does not distinguish the graphs if and only if they cannot be distinguished by a graph neural networks. So color refinement also describes or characterizes the power of graph neural networks. with respect to distinguishing graphs. And if you think about it, it's not very surprising, because in the end, color refinement does this message passing in an abstract way that the graph neural networks do in a specific way, somewhat more refined, but in the end, whether you say these are real numbers or just colors, in a sense, you can say color refinement is just an abstraction of what graph neural networks do. So the theorem is not terribly surprising. It's also not very difficult to prove. And it was proved at the same time by two groups, one me and my students and some other students, and another group at Stanford mainly. The proofs of these two results are quite different. The Stanford people use a universal approximation result for neural networks. So their result is a bit more general in terms of the neural networks it involves. Our result has the advantage that the neural networks we get are of polynomial size in terms of the graph, whereas theirs can get exponentially large. So anyway, we have this basic theorem, but still I think it's a very nice theorem because it connects the graph neural networks with a simple combinatorial algorithm. Okay, now we know that the color refinement algorithm is related to the logic C2. And so now we also get a logical characterization of graph neural networks. Graph neural networks can distinguish two graphs if and only if the logic C2 can distinguish the graphs. But actually, we don't always want to use graph neural networks to distinguish graphs, but we want to express properties of graphs or functional graphs. And what these guys showed here, Barcelo et al., is that if we have an isomorphism invariant property of graphs that is expressible in the logic C2, then it can be expressed by a graph neural network. Okay? Now, this is on the graph level. There's also a variant of the theorem for node properties. And there's also converse of the theorem. If the properties we look at are expressible in first order logic. Okay. So that gives us a very good understanding of the expressiveness of graph neural networks in terms of logic. Okay. We can extend this to the higher dimensional version of the Weisfeiler Leman algorithm. Actually, we took the higher dimensional Weisfeiler Leman algorithm as an inspiration to introduce higher order graph neural networks. And then we have the same kind of equivalence. And interestingly, so these higher order graph neural networks were inspired by this theory and this algorithm we knew from graph isomorphism testing, but then the work in chemical engineering I mentioned in the beginning, computing the octane value of molecules, that's based on these higher order graph neural networks. So the distance from fairly abstract theory to practical work is very short. That's quite nice. And again, as a corollary, we get essentially that these higher order or order K graph neural networks have the same expressiveness as the logic CK plus 1, the K plus 1 variable version of my counting first order logic. Okay, now there's one last thing that is quite interesting. Instead of giving the node initially a fixed state like the all-one vector, we can also initialize them randomly. That's something that is very often done in practice, just because it works well. Okay, and that's something we observed in our own work. And we started to analyze this. So let's say we the initial states are distributed in some way, say a normal distribution. It doesn't really matter which distribution we take. Okay, so of course, then we lose our invariance properties to some extent, because one run of the graph neural networks depends on the initial random distribution. So not only on the structure of the graph, it's not invariant, but as a random variable, these things are still invariant. Okay, so that's in a sense good enough. The functions are still reasonable, and we can repeat the argument and then average or whatever we do, and we get usually good concentration results and good values. Okay, it has been observed in practice and also studied systematically that they are substantially more expressive than graph neural networks. So random node initialization adds expressive power to the graph neural networks. This can clearly be observed in practice. And Sato et al., Sato, Yamada, and Kashima have also proved that interesting combinatorial problems can be expressed by graph neural networks with random node initialization. And then one thing we proved is that actually, once we add random node initialization, we can essentially express all invariant functions on graphs. So that's a universal formalism for graphs. Okay, and that's of course a satisfying result. So the graph neural networks can, in principle, express everything we want. Of course, there's still the question: can we learn these functions? And we cannot learn all functions. That's also clear. But on the other hand, we can do a lot, and that has been confirmed experimentally. Okay, there's also a node level version of this result I don't want to talk about. One thing to note is that these approximation results are non-uniform. That means for every size of the input graph, we get a separate graph neural network. Otherwise, we don't know what happens. Okay. So let me leave it there and briefly go to the second part of my talk about constraint satisfaction problems. As I said, this is fairly practical work. And let me tell you first what constraint satisfaction problems are. Well, they are general framework, essentially a logical framework, although the logic is very simple, for combinatorial search problems. So the Boolean satisfiability problem would be a typical constraint satisfaction problem. Also the problem of solving a system of linear equations. Now, usually here we consider constraint satisfaction problems with a finite domain. So solving linear equations falls out of this unless we solve them over a finite field, which we may do. We may also be able to generalize this to infinite domains, but let's stick to finite domains here. So what's a CSP? Well, the task is we want to assign values from a finite domain to variables subject to certain constraints. Okay, that's fairly general, but that's what it is. Okay, and now a specific constraint satisfaction problem is given by its constraint language. And that's the constraint language just tells us which constraints can we use. Okay, and then we also have an optimization version, a maximization version of the problem, and there the objective is to satisfy as many constraints as possible. So we don't read the constraints as hard constraints, but just as soft constraints which are desirable, and we want to satisfy as many as we can. Okay, now initially in our work we focused on binary constraints, so each constraint only involves two variables. In some sense this is completely general, okay, because we can encode all constraint satisfaction problems by using binary constraints. Okay, so how do we represent them? Now the constraints over a domain D, a binary constraint, we can represent by a D by D matrix. And this matrix is a 0-1 matrix, a Boolean matrix, and just tells us which value combinations are allowed. So we have two variables, and now we say it's allowed that the first variable has the value 1 and the second the value 2. So there's a 1 in the corresponding matrix entry, but it's not allowed that the first has value 1 and the second value 3. So there's a 0 in the place. I'll show you an example. Okay, and then if we have an instance, we can represent it by a directed graph where the nodes correspond to the variables and the edges correspond to the constraints. So look at these examples. We have a Boolean satisfiability problem, 3 constraints, 3 variables, x1, x2, x3. They have values 0, 1. And for example, this red edge corresponds to the first constraint. And what does this matrix tell us? Well, the allowed combinations of values are that one of the 2 variables gets a 1. What is not allowed is that both variables are 0. Then the constraint is not satisfied. Similarly for the other. So maximum 2 satisfiability can be described as a maximum constraint satisfaction problem in this way. Another one is maximum 2 colorability. I'm coming to this in a couple of slides, and maximum cut is another very well-known problem there. Okay, now we have come up with an architecture, a graph neural network architecture for solving such maximum constraint satisfaction problems. Okay, it's applicable to all binary constraints, and the nice thing is we take the constraint language and compile it into a loss function that we use to train our neural networks. So somebody tells me I want a solver for this constraint satisfaction problem. We take the language, automatically translate it to a loss function. We use this to train the neural networks. Now, how can we do this? Don't we need training examples? Well, actually, the training is unsupervised. So we just need the graphs, but we don't need the solutions. So we have the constraint graphs, and we generate them randomly. We use that to train our neural network, and then we come up with a model. And another nice aspect is even we train it on small graphs, like 100, 200 nodes, but we can apply it to graphs of size up to 10,000. So that works quite nicely. So I don't want to talk too much about the experimental results, but basically it works compared to others, neural network-based CSP solvers, it works clearly better. Even it works sometimes better as specialized solvers. For example, our thing for maximum 2 satisfiability is better than any known solver for this, even if it's specialized for this particular problem, whereas ours is completely generic. We can apply it to any problem. Okay, and it's also quite efficient. And what I mean by this, it's efficient in the inference phase. Once I've trained it, it's usually much faster than specialized solvers for the problems. Because we can, it's just this message passing for a couple of rounds that runs very fast. Okay, so that's another plus. Okay, so much for this. And I think I'll skip the part where I describe how we do the translation to the loss functions. We can also generalize this from binary to general CSP. So that's something we're currently working on with the student. So as I said, we can in principle translate just CSPs to binary CSPs. But that may not be the most efficient way. That doesn't always work very well in practice. Instead, we design a different kind of graph neural network directly applicable to arbitrary constraints. And there we do not only translate the constraint language into the loss function that we use for training, but we actually translate it also to the network structure, to the graph structure where we apply our GNN. Okay, this is work in progress with my student Jan Tönshoff, but it actually looks quite promising. Now, the last thing I want to show you is an example that demonstrates how this works. And it's quite fascinating. So we look at the two-colorability problem on a grid. And two-colorability, the goal is to color the vertices of a graph, in our case, this grid, with two colors, in such a way that every edge, the endpoints of every edge get different colors. Okay, so the colors we use here are black and gray, and you see conflict edges are red. So whenever an edge has endpoints of the same color as this one here or this one here, it's a red edge. And we want to get rid of the red edges. We want to resolve the conflicts or the constraint violations. Okay, so initially it looks like this, just some random coloring. And then this is really what this learned algorithm does. And what you see is it does something quite reasonable. It pushes this conflict to the boundaries, actually to the corners of the grid, which is a reasonable strategy. But the interesting thing about this is just learned. So the algorithm that comes out is quite reasonable, but it's a learned algorithm. So the machine learning stuff figured out this algorithm by itself. And it's not clear to me how this can work, because there's a lot of coordination going on. So how do the inner nodes, the compute nodes, know where to push, where the corners are? From their perspective, everything looks the same. So it's quite fascinating that this works in such a coordinated way. Okay, and I leave it here, and that's pretty much what I had to say. Maybe just a few concluding remarks. So GNNs are a very flexible learning architecture, and that allows them to adapt them to logical formalisms such as CSPs, right? The stuff we've seen in the last part of the talk. We do have a good understanding of the expressiveness, but there are also interesting open questions regarding expressiveness, so interesting theory questions. In particular, when it comes to this issue of uniformity, by which I mean expressiveness results that hold across input sizes. So here's an open problem. Can we express all graph queries or all graph properties that are computable in polynomial time by a recurrent graph neural network with random node initialization? So I said recurrent graph neural networks can in principle express all graph properties, but in a non-uniform way. We need a different graph neural network for every input size. Here I'm asking, can we do it uniformly? Can we find one graph neural network for every property? Well, clearly we can't, but we maybe can for all properties that can be decided in polynomial time. And finally, I should also mention that these expressiveness results only tell us part of the story. We ask which functions can we express in principle. We're not asking how can we find actually these functions? How can we train the neural networks? And of course, that's also something that needs to be considered, but it was not part of the work I was looking at here. And I just leave it there. Thank you very much for listening.
Thank you very much, Professor Martin, for the interesting talk. Now, before we go on to the discussion session, I think the committee, Professor Eddie, have something for you. So, Professor Eddie, please.
Okay. Just a moment.
Shall I stop the screen sharing?
Yep. Yes, yes, please. Okay, now I would like to present you how colorful and how diversity of our Indonesian culture. So this is. Can you listen the song? Yeah. Okay. Hopefully you enjoy the song.
Thank you very much.
Okay. Okay, let's begin our discussion session. We have a question here in the chat box from Fawaz. Fawaz, would you like to ask Professor Martin yourself?
Okay, I would like to thank you. Thank you, Professor Finney. So I would like to ask, could you, Professor Grohe, could you please explain why your GNN with RNI may not approximate invariance uniformly, as you talked before in your slide?
I mean, that just comes out of the proofs. We can only prove a non-uniform result and not a uniform one. We don't know how to do this. However, it seems unlikely that we can approximate all functions uniformly just for complexity reasons, because in the end, the computation done by a graph neural network is always a polynomial time computation, because and not all functions are computable in polynomial time. Though one has to be a bit careful with the actual computation model, but that's certainly a reason why you can't expect this to hold the general approximation result.
I see. Maybe there's an additional question. So can we add, does there exist an additional properties for the graph invariant such that it kind of works uniformly? Maybe does there exist?
Of course, I don't know, but I doubt it. One has to be careful that, I mean, one can't have everything. That's in the end, functions can be very complicated, and we cannot expect to be able to approximate them by such simple formalism. So some restrictions we probably have to make. We always have to make.
I see.
And also there's I mean, mathematically, there's the issue, say, of compactness. Usually, these results are based on some kind of compactness assumptions, which we have in the non-uniform setting if we fix the input size, but not in the non-uniform. So all the approximation results I know of are usually based on some kind of compactness assumptions.
Okay, thank you for the answer, Professor Grohe. Thank you for such a time.
Okay. Thank you, Fawaz. And now we have Intan Sherlin who raised hand. You could ask your question.
Okay, thank you, Ibu Vini. First of all, I would like to thank Professor Martin. It's really an honor for me to be able to hear your presentation today about this graph neural networks, since, well, it does remind me of my study during my master degree in Maastricht University in the Netherlands. You know, it's Maastricht is very close to Aachen. It's just, I think, 1 hour more or less by bus. So we know that study on data science and artificial intelligence in Maastricht or in the Netherlands or in Germany especially is already quite broad and you know, it's really advanced. But in Indonesia, if I could borrow your statement, it's still in an initialization state. So for me, it's as a student in ITB, it's really nice to know that I could somehow link my previous knowledge on that data science that I've learned during my master with the graph theory, which is my current research research interest. So I couldn't wait to elaborate more on this topic. And about the question, I have one question for you. Is it possible if this research on GNN to be carried on a more theoretical approach rather than a practical approach, such as building the algorithm or the programming? Thank you very much, Professor Martin.
Sure, and I mean, I'm coming from theory and mathematics myself, so I'm mostly interested in the theoretical work, although I have done some practical work on this. But what I can actually show you is, let me just go quickly back to my slides, if only I can find them. Now I can't, that's strange. Where are here? That should be. Okay, can you see these slides? So if you look at this paper, and I have another one. I mean, this one here is mostly about the theory of what I talked about, and I have another paper on vector embeddings of graphs, a survey paper that appeared in last year's POTS conference. They are both starting points for a theory of this work, and there's very interesting graph theoretic and combinatorial questions. So the other paper, if you send me email, I can also send you the paper if you're interested. So there's a lot of very interesting open theoretical questions in this area, and it's certainly worth pursuing.
All right, thank you very much, Prof.
Okay, thank you very much, Intan. Okay. And also in the participants, there is Professor Ion Tomascu. Good afternoon, Professor.
Good morning,
Good
Professor
morning.
Ion Tomascu. How are you today?
Good morning. Good morning.
Okay.
Thank you for attending this these courses. It's been a long time not seeing you.
I saw Shurahmat. I saw Vincent. Relatively.
Would you like to give a comment about the presentation, Professor?
we invite you to give some comment. Professor Ian Thomascu, do you have any comment on this lecture?
Very interesting application of graph theory.
Okay, thank you so much.
Thank you, Professor.
Thank you, Professor Martin Grohe.
Okay, so for the other participants,
can I have a
have,
question? Finish?
Okay, Professor ready?
Yeah. Okay, so Martin, thank you very much for your wonderful and inspiring talk. I learned a lot about graph neural networks. I'm newcomer on these topics actually. I have 3 questions for you. The first one is how you to set up the graph neural networks. Is it depends on the problems that we are dealing with, or can be invariant to the problems? So this is the first question. And the second question, if we have some information on the edges of the graph, so how we do incorporate this information, for example, because I saw in your model, you only having some information on the vertices on the nodes here. So how to collaborate or how to incorporate if we consider some information on the edges. For example, we have one of the conjectures, famous conjectures on graph theory, which is magic labeling on the tree. If is always the tree is magic or not, this is still a conjecture, big conjecture right now. So is it possible to deal or to solve this kind of conjecture using GNN with random node initiations? And then the last one, and the third one, I'm doing on Ramsey theory, and I'm just wondering, is it possible also to use this GNN to find the values of Ramsey number 5,5. That's all. Thank you.
Okay. Let me answer this. So your first question is, how do we set up these graph neural networks? Usually, it's different for every problem, and we have to run a lot of experiments to really make it work on the individual problems. So that's as a general rule. And you really, you have to play with the parameters. It takes a while to get this running. Usually when you start, whatever problem you start on, it doesn't work. And then you play with it, and in the end it works. That's my experience. And you have to know what to do. But we also try to come up with generic architectures like this constraint satisfaction, where you just translate the problem specification essentially to the graph neural network. So that's there. The idea is to make it easy to apply it without knowing a lot about graph neural networks. Then edge labels, there's 2 ways you can do this. One would be if you only have finitely many different edge labels, you can learn a separate message passing function for edges of each type. And the second is you can just basically introduce additional nodes for the edges. Imagine subdividing the edges and putting a node in between, and then you can put the edge label as a node label, and then apply our architecture. Both things work, and we have done both in practice, because indeed you very often have information on the edges, but you can deal with it. Now then the question, can you solve open conjectures in combinatorics using this? Well, one thing is, of course, you're limited to finite sizes. As with all computational approaches, you can never make statements in the limit. And then other than that, of course, you can try. In general, I think these methods do not work so well for intricate combinatorial settings, because it's, I mean, in the end, it's continuous optimization methods that we use. And in practice, problems tend to be somehow in a way that these methods work. I doubt they work very well on difficult combinatorial problems, but that's something to be tried. And so actually that's something I'm sometimes doing with my undergraduate students in projects. So for example, now I have one who tries to factor integers, and basically you could crack crypto systems with this using GNNs, and I expect this won't work. But in principle, you can all encode this in constraint satisfaction problems, and then just run our solver and see what happens. And you can do this with many problems, but in the end, I think the problems that are inherently hard, you won't be able to solve. You will be able to solve problems in practice, which are not hard, but you just don't know what to do. It's unknown structure, but usually the machine learning algorithm will find this unknown structure, and there they work. If it's really hard problems, I doubt it that it works, but in the end, you can only try.
Okay. Thank you. Thanks a lot.
Next question from Dr. Dinopia.
Okay, thank you, Bu Vini. Can you hear my voice?
Yeah.
Okay, Martin, this is just a continuation of, hi, Iwan. This is a continuation of Eddie's question. So, do you know any result using GNN in constructing combinatorial objects with known parameters?
No.
For instance, distance regular graphs of certain parameters, or probably the Moore graphs at degree 57. That's a big problem. Do you know?
No, I don't know any such results.
Okay.
As I said, I somehow doubt that that it's a good idea to use them. I don't know. I've never tried. But yeah, but again, my answer is all you can do is try it out. And I mean, whenever you use these, don't be discouraged if initially it doesn't work. That happens all the time. So also in our very practical projects, we start and the results are miserable, and then we look at the parameters and so on, and then in the end it works. That's how it is. But it seems to me that the problems that we're dealing with are usually fairly easy problems compared to hard combinatorial constructions.
Okay, thank you.
Is there any question? If there is no more questions, so I guess the discussion sessions, we will end the discussion sessions here. Thank you, Professor Martin, for the talk and the discussions. It was a very enlightening presentation.
Thank you very much. Thank you for inviting me. Okay.
I will give back to Professor Eddie.
Okay.
Stage.
Okay, so thanks again to Professor Martin Grohe for wonderful and inspiring talk. And on behalf of the ITB, Institut Teknologi Bandung, we would like to present you, Professor Martin Grohe, a certificate of combinatoric to this series, and also some nice drawing from our student. Okay, so let me present you from my screen. Okay, so this is the certificate of your talk today as a keynote speaker. And then I'll also present you some nice drawing of your photograph.
Okay, thank you.
Okay, so thank you so much again for your talk and for your time, your willingness to be with us today. So I think everybody here enjoy very much for your lectures. Okay, thank you. And thank you to everybody here for your time, and probably see you next 2 weeks. We will have another series of this combinatoric today series. Okay. Okay. Bye-bye, Professor Martin Grohe.
Thank you.
Thanks a lot. Yeah, good morning there. Still good morning. And okay, hopefully next time, if we would like to invite you to come to Indonesia, you will be willing to come here, right?
We'll see. Okay, thank you very much.
Okay. So okay. Thanks a lot.
Bye.
Yeah, bye-bye, Professor Martin Grohe. Yeah. Professor Ian Thomasku, thank you so much. We miss you. It's nice to have